Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to talk on module Structure of Ceramics and we will be talking about basic crystallography and bonding. And this is under the paper Ceramics. So after completing this module, the students will be able to learn about the fundamentals of point lattice, motif and crystal lattice. You will be able to gain understanding of crystal systems, Bravais lattice and relation to symmetry. The basics of bonding in material will also be given in this module. In this module, we will first briefly review the structure and bonding in materials in general, followed by a brief discussion on how atoms are packed in solids and what are the types of interstices present in various structures. Then we would briefly look at the types of bonding with reference to the nature of materials. Together, this information will form the basis of structure in ceramic material which are typically bonded with the mixed ionic bonding and covalent bonding. Subsequent, we would discuss the structure of ceramic materials with purely covalent bonding, followed by rather detailed description of ceramic materials with ionic bonding. And these are essentially based on packing of ions, closed packed forms where cations fill the interstices. So before moving further, we will first discuss about basic crystallography. So the first topic is point lattice. In a point lattice, there is a periodic arrangement of points in space and each point must have identical neighbors. In other words, a point lattice is a regularly spaced array of points and each point must have identical neighborhood. In the plane, point lattice can be constructed having unit cells in the shape of square, rectangle or hexagon. Unless otherwise specified, point lattice may be taken to refer to points in square array. Such an array is often called a grid or mesh. So you can see from the figure on the left hand side that the arrangement is irregular. There is no periodic arrangement, which is mentioned that no regular arrangement. So this is not a point lattice. Whereas adjacent to this figure on the right hand side, you can see a periodic arrangement or a regularly spaced array of points, which we have mentioned that it is a regular arrangement with identical neighborhood. So this is the example of point lattice. So we can summarize that a periodic array of points in space with each point having identical neighborhood is a point lattice. Let us take some more example. So on the extreme right hand side, you can see on the top side that this arrangement is not a point lattice because this is not a periodic arrangement and they do not have identical neighbors. Whereas on the bottom right hand side, the arrangement is a point lattice where all the points are identical. Similarly, a 3D translationary periodic arrangement of points in space is called lattice. Unit cell. As you all know that two non-collinear translations define a plane lattice and three non-coplanar translations define a space lattice. Now, the question arises that which pair of translations does one choose to describe it? In fact, there is an infinity of choices for each translation because a line joining any two lattice points is a translation of the lattice. So, on the extreme left-hand side, you can see a figure which shows a plain lattice and some of the choices that can be made. So, there are different combinations of unit translations in a plain lattice. Similarly, in 3 dimensions, it is convenient to consider a simplest parallelepiped formed by the primitive translation operation and is known as unit cell. The entire lattice then can be considered as an infinite collection of such unit cells repeated by its translation in all directions, which you can see from the figure which is in the middle. The unit cell can be defined as the smallest volume which when repeated in all directions builds the crystal. So the choice of the unit cell is not unique. According to the requirement of the case, either primitive or non-primitive cell can be selected as a unit cell. So the parallelepiped defined by translations A, B, C as the shortest possible sides along 3 crystallographic axes, that is X, Y and Z, is called a primitive cell. A primitive cell is a minimum volume unit cell and has only one lattice point in it. The volume of this unit cell is defined by A cross B dot C, which is by elementary vector analysis. Sometimes it is more convenient to choose a non-primitive unit cell depending upon the symmetry of the lattice. These cells contain more than one lattice point per unit cell. So, a unit cell parameter for a 3-dimensional unit cell are ABC and alpha, beta, gamma, which are the angles which are made by the 3 axes. Lattice vectors. So many unit cells can be formed, which we have shown in this figure by the cell vectors. This we have discussed in the previous slide. The lattice vector R can be represented as R is equal to N1 A1 plus N2 A2 plus N3 A3. The lattice parameters are usually defined by the translations which are A, B, C in directions X, Y and Z, and the second parameter for lattice is the angles, that is alpha, beta and gamma, which are made by the corresponding axis. Motif and lattice. So motif can be defined as a unit of pattern, and for a crystal it is an atom, an ion or group of atoms or ions, or a formula unit or formula units. As we know that a crystal structure is a combination of motif and point lattice, which we have discussed in previous slide. Motif is defined as a unit or a pattern. Often it is also called basis. When motif replaces points in a periodic point lattice, it gives rise to what is called as a crystal in a defined structure. So for example, on the left hand side of the slide, you can see a square lattice. So in this lattice, a periodic arrangement is there where a single dot is correspond to motif which are arranged in a square periodic pattern forming a crystal. The second example is adjacent to that is, it is a periodic arrangement but the motif is a hollow circle. Whereas in the third figure on the right hand side, you can see that this pattern is also a periodic arrangement, but here the motif is different. The motif is consist of two atoms, one is hollow and another one is the smaller one that is partially filled. Similarly, for the fourth figure, the motif changes for a crystal structure. On the extreme bottom right corner, the figure shows that the motif plus lattice forms a periodic pattern called crystal. So you can assume that when the motif is placed at the lattice points, they form a crystal structure. Now students, let us discuss about the types of lattice. So lattice can further be classified into two types, primitive lattice and non-primitive lattice. The primitive lattice have one formula unit or one lattice point or one unit of motif per unit cell, whereas the non-primitive cell have more than one lattice point or it have more than one unit of motif per unit cell, as you can see from this figure. On the extreme left hand side, the figure shows that a motif corresponds to a small animal which is repeated periodically and forming a structure. So this is a primitive unit cell where there is only one lattice point per unit cell. Whereas on the right hand side, it is an example of non-primitive unit cell where more than one lattice points per unit cells are involved. So we can find the volume of non-primitive cell which is equal to number of motif times volume of primitive unit cell. So one lattice point may contain one or more than one formula units of types of atoms depending on how they preserve the definition of lattice. Crystal systems in three-dimensional. As you can see that since choice of unit cell is not unique, we can define any unit cell of any shape as long it contains one lattice point. However, once starts defining various shapes, we come up with 7 categories called crystal systems in which all possible unit cell shapes would fit provided space filling criteria is fulfilled. So 7 crystal systems are known and shown in this figure. So the first one is a simple cubic, which is on the extreme top left corner. So this is the crystal system which has a cubic structure with A is equal to B is equal to C, means all the sides are same, with alpha is equal to beta is equal to gamma is equal to 90 degree. And the minimum symmetry in this is 4 3-fold rotations. The symmetries we will be discussing in the later on slides. The next is the simple tetragonal structure, where A is equal to B and not equal to C. Here, the alpha is equal to beta is equal to gamma is equal to 90 degree. Here also there is one 4-fold symmetry, that is rotational symmetry along the rotational inversion axis. The next is orthorhombic structure. In orthorhombic structure, A is not equal to B is not equal to C, and it has 3 perpendicular two-fold rotation along rotational inversion axis. Next term is monoclinic structure. So in monoclinic structure, A is not equal to B is not equal to C, and here alpha is equal to gamma is equal to 90 degree but not equal to beta, and here it has one two-fold rotation axis. Now comes the next structure, which is triclinic structure. In triclinic structure, again A is not equal to B is not equal to C, whereas the alpha, beta, gamma, all angles are not equal to each other and not equal to 90 degree. Next is rhombohedral structure. The rhombohedral structure is also known as trigonal structure. In this structure, you can see A is equal to B is equal to C. So that's why all the sides are shown as A. Whereas the angles alpha is equal to beta is equal to gamma is less than 120 degree. And here it has one three-fold rotation axis. The next is hexagonal structure. In hexagonal structure, A is equal to B not equal to C, and alpha is equal to beta is equal to 90 degree and gamma is 120 degree. Here it has one six-fold rotation axis which is along the rotational axis. Now comes Bravais lattice. So in order to specify the given arrangement of points in a spaced lattice or of atoms in a crystal, it is customary to define its coordinate with reference to a set of axes chosen with its origin as a lattice point. The three axes ABC and the opposite angles alpha, beta and gamma are already discussed in the previous slides. Further, each spaced lattice has a convenient set of axes. However, only 7 different systems of axes have been found, which are already been discussed in the previous slide and are representing all Bravais lattice. Accordingly, 14 spaced lattice are divided into 7 crystal systems. They are triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal and cubic. So all these structures are shown in this slide. If a crystal has no symmetry, then the point group is 1 or a center of symmetry is 1 only. Then there is no restriction on the shape of the unit cell. All 3 angles alpha, beta and gamma have to be specified, and hence the system is called triclinic or occasionally called an orthic system. A monoclinic crystal has two-fold symmetry in one direction only. One crystallographic axis is taken parallel to the direction of two-fold symmetry axis, and the other two axes must therefore be perpendicular to it. The choice of the cell is therefore restricted to a parallelepiped having 2 right angles. One angle has to be specified, hence the name monoclinic. Similarly, the other structures, that is orthorhombic structures and tetragonal structures, are already been discussed and mentioned in this slide in detail. Now students, here comes symmetry in crystals. The division of crystal structure into various crystal systems and Bravais lattice is based on symmetry considerations. Symmetry is an operation which brings the object back to its original configurations. The symmetry elements underlying a point lattice, which we will be discussing in the later slides with the examples. So there are basically 4 types of symmetries which we are categorizing here. So the first is reflection. So the reflection is across the mirror plane. The next is rotation. The rotation around a crystallographic axis by an angle theta such as 360 degree by theta is an integer of value 1, 2, 3, 4 and 6 and is termed as n-fold rotation. The next is the inversion symmetry, which is a point at xyz becomes its equivalent at -x, -y and -z. The next and last symmetry which we are talking here is rotation inversion. So the rotation is followed by inversion or rotation reflection, that is a rotation followed by reflection. Now let us take the examples of symmetry one by one. So the first one is reflection, which is shown on the extreme top right corner. So if we look this figure, we find that a plane transforms left-handed object into a right-handed one and vice versa. The element of symmetry in this case is known as symmetry plane or a mirror plane and symbolically represented by the letter M. The mirror coincident figures of this type are known as enantiophorous pairs and are related by reflection across a plane passing halfway between them. If a crystal is cut along symmetry plane and put on a mirror, the image will produce the other half of the crystal. So this type of symmetry is known as reflection symmetry, where point M reflects to point M2, which are same in both the cases. Next come inversion symmetry, which is inversion center, which is shown on the bottom left corner. This is a symmetry operation similar to reflection, with the difference that the reflection occurs in a plane of mirror, while the inversion is equivalent to reflection through a point called inversion center or center of symmetry. In other words, the pair of figures in this case is related by inversion center lying halfway between the two. Each point, that is M1 on one figure, is obtained from the other point, that is M2, by reflection through center and is symmetrically inverted. The complete figure therefore obtained is inverted completely. Thus, the inversion center or the center of symmetry has the property of inverting all space through a point. Next symmetry comes the rotation symmetry. In case of rotation symmetry, the symmetry operations which are encountered above, that is reflection and inversion, produce different sets of objects. However, it is also possible to have a rotational operation relating to such objects, and such an operation is called improper rotation. The corresponding symmetry element is known as improper rotational axis. There exist two improper rotations, which are rotoreflection and rotoinversion. So if we talk about rotation symmetry, for four-fold axis, M1 goes to M2, M3 and then M4. For three-fold axis, M1 goes to M3, and two-fold axis M1 goes to M4. So this is simple rotation. Next comes the rotation inversion center, which is shown on the extreme right corner, that is bottom corner. In this case, M1 becomes M1 dash due to four-fold rotation, and then inversion takes place where M1 dash becomes M2. Now comes interatomic bonding. The bonding in materials is a very important criteria and determines many of the physical properties of the material. For basics of bonding, you can refer to any elementary material science book, for example, Introduction to Material Science and Engineering, to get familiar with the fundamental aspects of bonding between atoms and how to determine the equilibrium separation distance, bond energy, and fundamental properties like Young modulus. Interatomic forces and potential energy. When two atoms are brought together, the force between the two varies as a function of their separation, that is R, which is shown in this figure. This can be plotted, which is shown on the right hand side. When the separation is large, there is a net attractive force between the atoms, dominated by Fa, which is negative. And when the separation is small, the atoms repel each other, dominated by Fr, which is positive. When the atoms are closer, the repulsive forces are high due to repulsion between the outer shell electron of two atoms, and when atoms are taken further away, they drop very rapidly. At a distance r0, these forces cancel each other, and this is called equilibrium separation between the atoms. At this distance, the potential energy of the system becomes minimum, which is shown in this figure, and the overall potential energy of such a system is represented by W is equal to minus A dash Z1 Z2 E square by R plus B divided by R to power M, where left hand side represents the attractive force and right hand side is due to repulsive force, which you can see from the sign also. The energy corresponding to the equilibrium separation is called bond energy, that is W0 of the materials, typically expressed in kilojoules per mole or EV per bond. It is the magnitude of this energy which is quite informative through the material properties and the nature of bonding between them. In general, higher the bonding energy is, higher would be the melting point, elastic modulus, hardness, and lesser is the coefficient of thermal expansion. So we can classify the bonding according to the magnitude of bond energy. The bonding in materials are divided into two categories. The first is primary bonding and the second is secondary bonding. The primary bonds exhibits bond energies in the range of 50 to 1000 kilojoules per mole. Primary bonds are metallic, covalent and ionic bonds, with metallic bonds typically being the weakest. On the other hand, the bonds with energies lower than 50 kilojoules per mole are called secondary bonds, and the examples of secondary bonds are van der Waals bond and the hydrogen bond. So, let's discuss about the primary bonding first. There are three types of primary bonding mechanism. So, the first is metallic, covalent and ionic. So, now the first bonding is metallic bonding. This type of bonding is characterized by presence of sea of electrons around atom in metal, and it is also known as free electron gas. The sharing of electrons is not complete enough to provide a covalent character and is delocalized. This very nature allows free movement of electrons around the metal cores whilst holding the cores together. This nature gives rise to a flexible bonds, good malleability, high electrical and thermal conductivity, and the example is shown in this figure. Typically, most elements to left to fourth column in periodic table show such behavior. Example of good metals are nickel, iron, copper, gold and silver and so on, and many other alloys are there. Most metals show a bond energy below 100 kilojoules per mole, which is a moderate energy, and this is why most metals have moderate melting points and elastic modulus with moderate coefficient of thermal expansion. Covalent bonding. In this bonding, atoms share their outer shell unpaired electrons, leading to a stronger and directional bonding, which is shown in this figure. An overlapping of orbitals is required for lowering of potential energy, which is typically facilitated by vacant spaces in the outermost orbital of bonding atoms. Typically, overlapping orbitals are directionally oriented, which further gets compounded by hybridization between overlapping orbitals, imparting a strongly director character to covalent bonds. For example, 2s and 2p orbitals in carbon form sp3 hybridization, which can hold a total of 8 electrons and facilitate sharing between neighboring carbon atoms in such a fashion that each atom is surrounded by 4 carbon atoms in tetrahedral combination, forming a regular tetrahedra. This leads to an interbond angle of 109.5 degrees and a strong directionality in diamonds. Examples of materials showing this bonding are primarily from group 4 and 5th elements and compounds such as silicon, carbon, germanium, silicon carbide, nitrogen, phosphorus and so on. And the bonding energies of some of the common covalently bonded materials are 176 kilojoules per mole for silicon, 347 kilojoules per mole for diamond. Ionic bonding. This bonding occurs due to two positively charged elements, for example in NaCl, MgO, ZnO and so on. The electron transfer from one ion takes place to the other ion. Higher the difference between the tendency to accept and give away the electrons are described by the difference in the electronegativity, resulting in the stronger bond formation. Due to spherical symmetry of atoms and thus the bonding force around the atoms, ionic bonding is not directional in nature. To begin with, ions can be treated as a point charges, and when two charges are brought closer to each other, the attractive force between the two can be written by the Coulomb's law, which is minus A Q1 Q2 by R square, where A is a constant. Q1 Q2 are the charges on each ion and R is the separation distance. That is, the resulting potential energy can be written as minus A Q1 Q2 by R. This attractive force varies as square of the distance between the two ions. However, when atoms are brought too closer to each other, their electron clouds start overlapping, and since Pauli exclusion principle cannot be violated, as two electrons can occupy the same quantum state. This leads to the repulsive force between the ions, and the total potential energy of the system can be expressed as minus A Q1 Q2 by R plus B by R to power M plus delta E, where B and M are the constants determined empirically and B by R to power M is the repulsive energy. Delta E is the difference between the ionization potential of cations and electron affinity of the ions, which is typically a very small number. So the bond energy is determined by taking the first derivative and equating to 0. From there we can find W naught at an equilibrium distance of R naught. This type of bonding typically leads to high bond energies, and as a consequence, ionically bonded materials typically exhibit high bond strength, high melting point, high elastic modulus, brittle nature, low thermal and electrical conductivities. Secondary bonding. The secondary bonding arises from the interaction between the charged dipoles. The magnitude of this bonding is typically below 50 kilojoules per mole and even below. These arises due to fluctuating dipoles. The dipoles interaction leads to such type of bonding. The first kind of between fluctuating dipoles, and it is observed in gases like hydrogen, which is shown as an example in the figure. The second type is the induced by the existence of permanent dipole moment induced due to the presence of permanent dipoles in the materials, such as on polymers, where within a chain units are covalently bonded, while between two chains secondary bonding exists, and it is shown on the right hand side. Typical examples of materials showing secondary bonding are water, which has the energy of 20.5 kilojoules per mole, ammonia and HF. So students, let's now summarize what we have learned in this module. So we have learned firstly the point lattice, and the point lattice is regular arrangement of points in a space within identical neighborhood. Then we have discussed a motif. A motif is similar to a unit or basis. It replaces the point to create a crystal structure, and a unit cell is the smallest repeatable unit which we have learned in this module. So the unit cell containing one lattice point is called a primitive unit cell, and the one having a group or more than one lattice point is called a non-primitive cell. There are total 7 crystal systems and 14 Brevis lattice which we have discussed in this module. Further, we have discussed about the bonding. We have discussed that the bonding are of two types, primary and secondary. We have discussed the ionic bonding, and in ionic bonding the bond energy is larger and it has larger alpha values. For example, in case of MgO, it is 1000 kilojoules per mole. Whereas in covalent bonding, the bond energy is variable. For diamond it is large and for bismuth it is small. Next is the metallic bonding which we have discussed. In this bonding the bond energy is variable. It is large for tungsten, small for mercury and moderate for aluminium. It varies over a large range. Whereas if we talk about secondary bonding, the bond energy is very small, which results to directional interchange and intermolecular bonding.